Discover why time passes differently for observers moving at different velocities through Einstein's special relativity. Time is not absolute. It flows differently depending on your velocity, a mind-bending consequence of special relativity. The principle that explains this phenomenon is called time dilation. Time dilation states that a clock moving relative to an observer appears to tick more slowly than a clock at rest. The mathematical formula is delta t prime equals delta t divided by the square root of 1 minus versus squared over c squared. We call this factor gamma, the Lorentz factor, which determines how much time dilates. In these equations, v represents the velocity of the moving observer, and c is the speed of light. Time dilation emerges from Einstein's two fundamental postulates of special relativity. The first postulate says physics laws are identical in all inertial reference frames. The second postulate states that light speed is constant for all observers. These two simple postulates have a shocking consequence. They force time itself to be relative rather than absolute. Let's understand time dilation through the famous light clock thought experiment. Imagine a light clock. A photon bounces between two mirrors. Each bounce is one tick of the clock. When the clock is stationary relative to you, the light simply travels straight up and down between the mirrors. But when the clock moves horizontally, the light must travel a diagonal path to catch up with the moving mirrors. Now we can see why the moving clock must run slower. The key insight: the diagonal path the light travels in the moving clock is geometrically longer than the straight vertical path. The diagonal distance is greater than the vertical distance. However, Einstein's second postulate demands that light speed must be exactly the same for both observers, since speed equals distance over time and the speed of light is constant. If the path is longer but the speed is the same, then more time must have passed for the moving observer. Therefore, the moving clock must tick slower to accommodate the longer path at constant light speed. Let's derive the exact formula for time dilation using geometry. We can form a right triangle. The vertical side is the distance d, the horizontal side is the distance the clock moved, v times t prime, and the hypotenuse is the diagonal path, c times t prime. By the Pythagorean theorem, c squared times t prime squared equals d squared plus versus squared times t prime squared. For the stationary observer, the distance is simply c times t. Substituting, c squared t prime squared equals c squared t squared plus versus squared t prime squared. Rearranging, c squared t prime squared minus versus squared t prime squared equals c squared t squared. Factoring out t prime squared times the quantity c squared minus versus squared equals c squared t squared. Taking the square root and solving for t prime equals ct divided by the square root of c squared minus versus squared. Dividing numerator and denominator by c, we get our time dilation formula. Let's explore what the Lorentz factor gamma actually means. Here's a graph of the Lorentz factor gamma versus velocity. At low speeds, gamma is close to 1, meaning almost no time dilation. At everyday speeds like cars or planes, the Lorentz factor is so close to 1 that time dilation is completely negligible. Even at 10% the speed of light, gamma is only 1.005. But as velocity approaches the speed of light, gamma grows rapidly toward infinity, causing extreme time dilation. At 90% light speed, gamma equals 2.29, so time passes more than twice as slowly. At 99% light speed, gamma jumps to 7.09. The famous twin paradox illustrates time dilation dramatically. Twin A stays on Earth. Twin B travels at high speed to a distant star and returns. Due to time dilation, twin B ages less than twin A. The traveling twin experiences less elapsed time and therefore ages more slowly than the twin who stayed home. The time experienced by twin B equals the time experienced by twin A divided by gamma. Time dilation isn't just theory. It has been verified experimentally many times. Muons created in Earth's upper atmosphere should decay before reaching the ground, but time dilation extends their lifetime from our perspective. Atomic clocks flown on airplanes have been measured to run slower than identical clocks left on the ground. GPS satellites experience time dilation and must correct for it, otherwise navigation would accumulate huge errors. In particle accelerators, we observe that fast-moving particles live longer than their stationary counterparts due to time dilation. Let's summarize the key insights about time dilation. Time is relative, not absolute. Light speed is constant for all observers. Moving clocks run slower, and the effect grows dramatically as speed approaches light speed. Time dilation is not science fiction. It's a real, measured phenomenon that we must account for in modern technology. Time dilation reveals that space and time are fundamentally connected, forming a unified spacetime. Special relativity teaches us that we live in a four-dimensional spacetime, not separate space and time. Let's review what we've learned about time dilation. Time dilation is the principle that moving clocks run slower relative to stationary observers. This phenomenon emerges directly from the constancy of the speed of light for all observers. The magnitude of time dilation is quantified by the Lorentz factor gamma. Time dilation has been verified through countless experiments and is essential for technologies like GPS.